Comments, questions, concerns about any of those 5 questions? Going once, twice, thrice, sold. Okay, 2 more reaction types, and then we will look at some demos of these things. We've done synthesis and decomposition. Synthesis took 2 simple things, made a larger, more complex thing. Decomposition did the opposite. It took a large, complex compound and broke it up into simpler pieces, either polyatomic ions or simpler compounds or just the raw elements themselves. Then we looked at single replacement. Single replacement took an element or an ion and it reacted it with a compound and it swapped out one of the pieces of the larger compound. If the ion or atom or whatever it is was positive, it swapped with the positive portion of the compound. If it was negative, it swaps with the negative portion of the compound, kicks it out of its relationship, for lack of a better analogy. And then double replacement was a direct swap. You have a compound and a compound. The compounds are not satisfied the way they are, so they swap partners. Get compounds that are more stable. Now, today, this is going to be a quick one because we've looked at it already. This is, what am I looking for here? The 5th reaction was a synthesis, decomposition, single replacement, double replacement. The one that we've already looked at. What's it called? Come on, guys. What's the next reaction type? The acid-base neutralization. We've already done this one in a lot more detail. So just generally speaking, a neutralization is always an acid plus a base, and the products are always the same. You're always going to get water, and you're going to get some form of salt. A salt. Whatever it happens to be. So generally speaking, we can use the generalized forms for this. The general form for an acid I gave you was something like HA, where that hydrogen out front denotes the fact that you have an acid. Definition of an acid, something that gives up a hydrogen ion when you put it in solution. Your generic base is BOH, so that when these guys come together, you're going to get HOH, also known as H2O, your water. And what's the formula going to be for the salt in this general case? It's going to be Ba. Whatever those pieces are from their respective acid or base, those guys are going to get together to form the salt. So an example, we've talked about it a few times. You've done this one. HCl plus NaOH produced NaCl, table salt, and HOH, water. So I don't even necessarily think we need a ton of time here. For all 4 of these, what's the first product going to be? Water. So we can just go ahead and write H2O for all of them. And then we can go back and we can make the salt. What's the salt from the first one? Anybody? It's going to be NaBr. You take the positive ion from the base, you take the negative ion from the acid, you look at their charges. In this case, the Br has a charge of -1, the Na has a charge of +1, which could be sodium bromide, NaBr. What's the second one? The second one's going to be a little bit more complicated. It's going to be Mg3 bracket PO4 close the bracket 2. You betcha. The magnesium has a charge of +2. The phosphate has a charge of -3. Swap and drop the charges. Get your compound, your salt in this case. The next one. It's going to be PbCl2. Very good. Lead is one of those ones that's multivalent, so you have to look at how many hydroxides there are to figure out what charge of lead you've got here. OH has a charge of -1, so there's 2 of them. There's only one lead. So that means your lead has to be positive too. So you need 2 chlorines to balance that out. PbCl2. And then the last one, you're going to take the H from the ClO4. You're going to take the OH from the aluminum. And then what's your salt going to be? Al bracket ClO4, close the bracket 3. Very good. Comments, questions, concerns on how Brooklyn did that, because Brooklyn did all of them. I don't even have to specify which one because there's 4 of them. I have a 1 in 7 chance of getting it right just by saying Brooklyn did it. Questions, comments, concerns? Any of those? Acids, bases? This is the second time we've looked at it. Are we all cool with how these things were formed? Are we getting more comfortable with building these compounds? Some of you are answering. Some of you are just smirking, which doesn't fill me with a ton of confidence. Okay, last one. The combustions. Combustion reactions. So combustions are interesting. Combustions require a class of compound that we have kind of talked about. I alluded to it once. We're going to talk about it in a slight bit of depth here today. Combustion reactions require an organic compound. And I'm going to define that for you here. You require an organic compound. You're going to take that organic compound, you're going to react it with oxygen. Usually to do that, you have to add some form of heat. And the products for these guys are always the same. Before we tell you what the products are, let's look at what an organic compound is. When I say organic, what comes to mind? Fruit and vegetables. Organic produce raised without the use of pesticides. It's all a scam. That's not what I mean by organic. It's not always a scam, but I've worked on farms. I've seen the darker side. Yeah. 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 That's why we get it at Costco. Yeah, I know, but you do what you got to do for your 4-year-old. That's why you do it at Costco, because it's cheaper. And now we have pink sea salt for decades. No, that's never going to happen. No. Organic compounds. Okay, so on one side, organic is your produce. It's your pesticide-free, no GMO, you're paying more and getting an inferior product kind of scenario. Organic shows up in other places. What other place have you, or maybe you haven't, heard this term organic? Yes, Evelyn. Okay. When you're talking about something original, perhaps? Yeah. Do I have any sci-fi buffs here? No science fiction nerds? Not one of me? No? Okay, cool. The other place that organic shows up, and that's where I'm trying to guide you towards, is when we talk about life forms. Like life as we know it can take one of a couple forms. You can have organic life, which you guys are because you are made up of compounds that are scientifically classified to be organic, and then there's inorganic life that are not made up of these kinds of compounds. And if you've never heard that, that's fine. That's where I was trying to get us to. The definition for organic in a science class is an organic compound is a compound made of hydrogen and carbon, primarily. You can toss other things in there, but primarily it's hydrogen and carbon. Sometimes you can toss in oxygen. You can toss in other things in there too. But you guys, we are, as a human race, we are a carbon-based life form. Carbon shows up all throughout both the processes that you require to live, cellular respiration being the big one, for those of you who remember back to Science 9, and carbon's found in all of the molecules, or not all, most of the molecules that make you up. So when we talk about organic compounds, the big three that I have listed before, but we'll list them here again. The first one are what are called hydrocarbons, compounds made up of just hydrogen and carbon. These are things like propane, methane, butane, anything that ends in ANE, octane, which is a fuel additive, anything that ends in ANE, these are your hydrocarbons. Methane, propane, heptane, octane, hexane, ethane, all of these are hydrocarbons. The next group are what are called alcohols. Alcohols are things that are named, the ending is OL, methanol, ethanol, propanol, which you might know as better as isopropyl alcohol, also called rubbing alcohol, stuff that burns when you, well, that's not the hydrogen peroxide. The isopropyl rubbing alcohol that you find in hand sanitizer, for example. All of those are considered alcohols. They are all easy to combust. You got your hydrocarbons, you got your alcohols, and you got your ethers. Some of you are fond of your ethers more than perhaps you should be, especially grade 9 boys. Very fond of the ethers. Ethers are smelly compounds found in perfumes, deodorants. Axe body spray is the one that I'm referencing there. Yeah. Ethers, their names all end in ENE. So the organic compounds that we look at are the hydrocarbons, the alcohols, the ethers. There are more, but these are the big three. All of them are fantastically flammable. It's why Axe body spray is so flammable. It's why you can, gasoline is flammable. Alcohol is flammable, which I'm going to show you today. And the generalized form for these guys, you're always looking for an organic compound plus oxygen. Now, they always have the exact same two products. When you burn an organic compound, what do you produce? Who knows? Let's look at the generalized form. Perhaps you can tell me. So the generalized form here is going to be something like CXHY. So what I mean here, CXHY, this is your generic hydrocarbon. You can have X carbons, and Y hydrogens, an unknown amount of these guys bound together in a compound. It could be CH4, that's methane. It could be C2H6, that's ethane. It could be C3H8, that's propane. It could, these X's and Y's can be certain sets of numbers. They will always react with O2. Now, take a look at those three elements. What two compounds can you, what two very common compounds can you make from those three elements? Louder, Rob Kirk, was that you? Or was that Nielsen? What can you make of very common compounds you can make of carbon? You're making both of them right now. As you sit in your desks. Carbon dioxide is one, and water is the other. Every single combustion reaction has at least those two products. Now, depending on what other reactions are going on beside the combustion, there might be additional reactants, there might be additional products. But every combustion reaction is going to take in an organic compound. It's always going to produce CO2 and H2O. That's why perhaps you've seen liquid dripping out of the back of a car while it sits out of the exhaust while it sits there on island, because the burning of the gasoline in the internal combustion engine produces water vapor. You don't see it as liquid water because it's hot inside an engine, it's vapor. But as it goes down the exhaust pipe, it cools, it condenses, it becomes liquid again. There's not a problem with your car if you have water leaking out the back. It's a product of combustion. Another example would be a generalized form. If you don't have a hydrocarbon, the generalized alcohol and ether have the same general form. It's CxHyOZ plus O2. And the products are always the same. It's always going to be CO2 and H2O. Now, an interesting example of this, well, I've got 4 for you down here. 5 of them. But the one I wanted to draw your attention to here is letter D. Letter D, who recognizes that reaction? C6H12O6 plus O2 wasn't a lab. Any of you who had me in grade 9, I make a big deal about talking about this reaction. It is the opposite of the reaction that you referenced yesterday. You said, when I was asking you guys about synthesis, everyone's big example, your block and C block, everyone said, oh yes, photosynthesis. None of you could tell me what it was, except for Numrit finally was able to do it. Photosynthesis is you take in sunlight, you take in water, you take in carbon dioxide, and a plant will use this to produce a carbohydrate, glucose, C6H12O6. Cows go, and it produces oxygen. Now, the opposite of cows go is so that's what plants do. Your guys' process is the opposite. It's cellular respiration. You take in carbs. Your body needs glucose, sugar, C6H12O6. You breathe in air. The only part of the air your body actually uses is the oxygen, and you turn around and you produce water that leaves your body in the form of sweat and urine, and carbon dioxide, which you breathe out. This is called cellular respiration. Arguably the most important of all the combustion reactions. And so what that means is all the time inside your body, this combustion reaction is happening. If it stops, you die. And so you don't necessarily think about combustion reactions in this way. You think of the flashy ones that I'm going to show you today. But this one is a combustion, absolutely necessary to keep you alive. Yeah. If it's not as efficient, you will live slower. You know, that's the other way to talk about it, yeah. Yeah, I mean, if your body just decides to stop cellular respirating, this is the process that keeps you alive. It provides you with, so photosynthesis takes in a form of energy that we call, well, that's light, sunlight. This process produces an energy molecule called ATP. If that doesn't exist, your body doesn't function. You die at the cellular level, which would be awful. But every combustion has the exact same products. C3H8 plus O2, H2O plus CO2. C4H10 plus O2, H2O plus CO2. C2H4 plus O2, H2O plus CO2. And last but not least, C12H22O11. I don't know what that compound is. I don't remember. My organic chemistry was a long, long time ago. But it's organic, and you react it with oxygen. You're going to make, every time, H2O plus CO2. The products are always the same. Now, balancing these things, this is, if you recall back when I gave you balancing, lots of balancing practice over 3 or 4 days, the grossest ones were almost always these. That's the hard part of a combustion. The products are easy. Figuring out in what proportions they react, that's where things get a little bit sucky. Okay, so, yeah. I'm going to demonstrate some of these because, you know what? How boring would it be if we just talked about the reactions? We never actually did any of the reactions. So, we can go outside today too. Let's do it. We're going to do a few of them in here, but we're going to do one of them outside because it's real dangerous to do inside. Use my lab coat. So, if you could close your binders for a sec, because I'm going to use your guys' tabletops for this, for these different reactions. And we're going to get you up, moving around, because I want everyone to see what's going on, so I'm going to do it out in the world. By out in the world, I mean among you. Okay. So, let's do this. Say, hey, you want to give me a hand? Yeah. Can you grab the orange extension cord from over there? And if you could set it up with this guy, that guy, over here, this one. Okay, so you can plug it in behind the calculators. We'll do that guy there. Sarah, Sarah. Would you mind going to go? No, what? No, I don't want to. Matthew, could you go get the scale on the back of the glass there? You get this. Sarah, you can come here and get this guy and this guy. And Amatoji, if you could go over there and grab me. If you could grab the big it says delete off. It's upside down there, up next to the window. Oh no, the guy on the back windowsill. No, on the back windowsill. Yeah, take that to your desk, sir. Oh yeah, this guy. Yes, a graduated cylinder from over there. A 20 mil, we have one. That was that table as well. Okay, so you guys have the neutralization. You guys have the decomposition. You guys have the synthesis reaction. You guys are going to get the double replacement reaction. Where's my double replacement? This guy. Did you go to the lab? Yes. Grab me 2 more 100 mil graduated cylinders. And no, forget it. Don't worry about it. Just 2 more of 100 mil graduated cylinders. Would you mind, Angel? I'm gonna grab this guy. Massey. I'm gonna get you to come grab this guy. That guy. And Brooklyn. One of the 3 of you. You know what? No. Evelyn. Come grab this. Okay, and then this guy is gonna go sit by the door. This is the most dangerous part I've ever been allowed to push around the whole no, where are you going? Your desk. Oh, where are you going? Okay, your desk, except I need the lighter back. I'm taking my reaction and I'm going home. Okay, synthesis reaction. Let's do that one first. Synthesis reaction is, they happen all the time. They're relative. Where'd the tray go? They're relatively straightforward. Well, Massey, I forgot to do one more thing. You get this guy. Synthesis reactions take simple compounds, simple elements or simple ions. They combine them together. So a simple example of this would be something like rust.
which happens all sorts of different ways, but a more interesting example is this. I don't know if you've ever done, have you ever played with a 9-volt battery and like touched it and stuff? Or licked it? None of you have ever done this? You licked a 9-volt battery? No, no. Seriously? Nothing will go wrong, I promise. Go home and lick a 9-volt. Okay, so I have steel wool here. Steel wool is as pure iron as you can get. It's like an SOS. I don't think you ever play with an SOS pad. You know what these SOS pads are? No? Okay, they're the blue pads. Sometimes your parents might use it to clean or leave that pan. Leave like baked on. Yes, you've seen these things before. Okay. So steel wool is this without the soap. It's just straight iron. So what I'd like you to, and for all of these reactions, get up around the area that we're doing these things at. Those two, what's that there? Yeah, and so some of these are going to be more interesting than others. This one's not particularly flashy. So what we're going to actually, you guys need to see that a little bit. What we're going to do is we are going to take the steel wool and we're going to react it with the air. We react it with the air by lighting it on fire. Now with steel wool, it's like steel wool's not going to burn. It does. And watch what happens to the mass. Working rates was right. A little better. Nothing to mass. Right. Another. Ooh, why is that?
That's what I was thinking.
So this is still well, what can happen? Once I explain it, actually see what the problem is. Okay, now we got. One of you had tongs with your maximum. 1 gram to start. color on this side than it is on the other side. Yeah. Nope. What color is it on that side? Blue. This side is stuff that hasn't had a chance to burn. And the mass has gone up. It was 1 gram exactly. Why is the mass gone? Even just a little bit. Why has the mass gone? Why? Not a formula. It's gone up 0.03 grams, which is not a lot, but it's not insignificant. What is being added to the steel wool? Oh, there we go. We have enough. Oh, it's trying to go up another 100th of a gram. The pieces of fire. Okay, we haven't gone up a lot. Not a very dramatic one, a reaction nonetheless. When you burn something, what is the reaction? Steel wool is just iron. Reacting with the oxygen in the air. So what's the 0.03 grams that got added to the meth? Excuse me, of the steel wool? It's this. It's these oxygen atoms that are binding with the iron. That's why you get something with a new color. When you guys talk about, when you do chemistry in Science 9, you talk about how chemical changes can be indicated by a color change. It was this color, now a lot darker. So what we created on the top was a layer of iron oxide. Basically, I just made it rust really fast. So that is an example of a synthesis reaction. Not a very dramatic one, but a synthesis reaction nonetheless. Okay. Another one. Let's look at decomposition. Yeah. This one's more impressive. Okay. Okay, so we open up that container. That guy right there. This is dramatic enough. Okay. I graduated cylinder. Can you bring me the graduated cylinder from over there? Again, the big thing with the yellow base. Okay, here we go. Let's see how much we got. This is hydrogen peroxide. This is you guys may have had the misfortune of having this placed on your cuts and stuff when you were a kid. The stuff that you can buy from the grocery store is 3% hydrogen peroxide. This is 30% hydrogen peroxide. This is, if you look at all of the material safety data sheets, it looks innocuous, but this is the single most dangerous compound we actually have in the lab. It does very nasty things to people, and so we're going to use it naturally. Let's see if I have enough. Okay. This is dish soap. Dish soap makes things more fun. You squirt some of that in there. A large squirt. Sure, yeah, like that. Love that. And our lab tech, Christy, decided it would be cool to add some food coloring. So let's add some. That might stain things. Hair. Okay, 2 drops. Let's see what happens. Maybe we stain things. Maybe we generate can add it. Okay. Green in there. And green, love that. Okay. So hydrogen peroxide on its own is going to decompose. Formula for hydrogen peroxide, you can see here on the bottom, H2O2. So H2O2 is going to decompose into hydrogen gas and water. Effectively, the extra hydrogen is going to leave. Now, it's doing it already as it kind of sits there. But it's more interesting if you speed the thing up. So I'm going to give you It's called potassium iodide. It's not a reactant in the reaction that you're about to see, because if you recall, the decomposition takes one compound and breaks it apart. That reaction is already happening here. You can kind of see bubbles forming on the side. That's gas slowly being produced from the hydrogen peroxide. What this is a catalyst. Now, catalysts just help things happen faster. So this particular catalyst is potassium iodide. It'll stain your skin and your clothes. So I'm not going to get you this. And when you pour it in here, it causes the hydrogen peroxide to decompose all at once. This demo is called elephant toothpaste. You've probably seen it before. But that's the science behind what's happening here. We just made the whole thing decompose all at once. It's steaming because it's really quite hot. No, I can say what I have left. But that's elephant toothpaste. Now, if anyone would like a chemical break, and this is what I've done in the past, you can actually touch this foam, and then let it sit in your hands for a little bit and go wash it off. Your hands will turn almost flaky and white as the hydrogen peroxide effectively burns. No, the actual chemical. So that's that guy there. Nice. That's definitely. Elephant toothpaste to decomposition. Single replacement. How much time do we have? We're going to have to do the single replacement tomorrow. I'm not going to tell you what the single replacement is because I don't want you to go Google it because it's pretty fun. We'll do it tomorrow. Let's do the double replacement. The double replacement is this guy over here. No, with 25 minutes left, I'm not going to do the outside one today. Because it's like toothpaste, but it's pink. That's what they call toothpaste for health. Makes kids be like, oh, I love it. So hey, you still my keys? Yeah. I need to go get another one of. Yeah, I need to go back to the lab real quick for that. Okay, gather around this desk and chat amongst yourselves. I'll be right back. Gotta watch it, bro. Trust me. Wait, you were listening to watch? Okay, so this reaction we're actually going to do in a large test tube. This is a double replacement reaction. Cool. Okay. Double replacement reaction. I need two people. Sure. Ellen and Robin. Each grab a graduated cylinder. You can go on that side, that's cool. And each of you gets one of those bottles. Yeah. You know what? They need a bottle. Small if you already set the bottle. Yes, you will. Okay. Actually, I need to graduate. Okay, which of the two of you has copper 2 chloride? Okay, cool. You get the big thing. Measure out 70 mils of that. 70. 0. You get to measure out 50 of yours. No. This would be bad for both of you. Copper chloride and sodium phosphate. No, don't do it. So you measure at 50, you measure at 70? Cool, love that. Okay, so take a look at the colors of these two solutions. If you can't see, it doesn't have to be exact, that's great. You can see kind of what's going on here. You've got like a light blue Kool-Aid kind of color. You've got water, basically. I'd like you to take yours and dump it in hers. So it got darker, and as it sits there, you're going to see something else happen. Take a look at what's going on at the bottom. It's clearing up. So you had two clear liquids. One was blue, one was like clear. And now you've got this kind of cloudy liquid. And you can kind of see this clearing up here at the bottom. But we're going to let that sit for a little bit and then come back to it. The double replacements aren't always super dramatic. But you very clearly have something different. Now, while that sits and does its thing, we're going to go over to Massey and the Heaps and Daniels table. I'll come back and take a look at what's happening there. Actually, no, I lied. We're going to go back to the Brooklyn's table. Okay. What? No, Olivia's table. Okay, so let that kind of sit and do its thing. This. Okay. Sid, can you grab my paper? That was stacked, yeah. Okay, I don't need more stuff. Start that over there. There. You. Running to the right one. Oh, front page has it all. Cool. So, decomposition we've done. The synthesis was kind of boring. The single replacement we're going to do tomorrow. The double replacement's over there. No, we'll go out of order. This is going to be a combustion reaction, but a combustion, you can take a look. A combustion reaction unlike any that you've perhaps experienced before. Here it is. Can you with your finger? Tell me what it is. Sugar, cool. We're not going to get you to do that with this because this is baking soda. Baking soda is gross. But we've got sugar, we've got baking soda. We need a smooth. This is not overly exact. You don't need bottles for this. 1 scoop of that, 4 scoops of that. Roughly similar size scoops. 1, 2, 3, 4. Okay, cool. Stir that up. Now, you don't expect anything to happen if you do this all. Those of you who bake at home have mixed sugar and baking soda together and nothing happens. Nothing's going to happen here. Now, pour that in the middle of this and I'll do pile. All together. This is lighter fluid. Liquid fire starter. Soak in there. Where'd my lighter go? Yep. And now we light it up. Should be. Put it on. Come on. Do your thing. Campfire. Oh. Yeah. No, don't dig in. There we go. Yes. You guys are all equal. No, it is a combustion, so you expect them to. Fire alarm goes off there. I don't know what to do. Next time I can use local firefighter. Yeah, Massey, you want to pass me that picture up? The liquid in it? Everyone slide back over. Well, it's not going to be huge, but this is ethanol, methanol. So it's alcohol. For those of you who don't know, alcohol burns real good. You don't want to drink this stuff because it will make you go blind. This is not a drinking alcohol. This is a. Oh, we go. That's what we wanted right there. See, now we use this. Okay, cool. Okay, cool. And now all the sugar and baking soda gets to react together. So it's not as dramatic as perhaps you'd expect. This is an example of a combustion reaction. The baking soda is providing oxygen to the sugar. And give me a place to put the liquid. No. Nope. That's what you guys are typically familiar with. What we're going to do next is what you typically think of when you think of combustion. No, it's exactly the same. It's sugar. It's C6H12O6, and it's reacting with oxygen produced by the baking soda, and it's creating these. Not working. That's awesome. No, this is not at all. This reaction is supposed to be called Paris. The vacuum is supposed to grow. Unless the semester actually had to grow, we gave it around and grew up. So I have to figure what went on this time. Hopefully next walk will be better. Okay. Not as awesome as it's been in the past, but still it's actually happening. We'll let that one keep going. See how long it lasts. Lights off, please. Lights off. The bottom switch. Yeah, that's probably. burning. This is also a combustion reaction. I'll save the acid-base one until tomorrow. This, as I said already, this is methanol. It's pure alcohol. CH4O. What we're going to do, who wants to do this one? We did a massive, sure, come on. Pick up the wood split. Grab the lighter with the other hand. What am I doing? So I put a little bit of alcohol in here, and when you take alcohol and you, as a liquid, like gasoline doesn't, I don't know if you know this, as a liquid, gas doesn't burn. As a liquid, alcohol doesn't burn, you need to fuse. So what I've done here is I've poured a little bit of alcohol in here, and I'm shaking it around to kind of aerosolize it. I want to fuse the buildup inside this jug. Okay, so what I want you to do is light this thing on fire. I'll light this thing on fire. And then wait on the safe distance away. I want you to drop this into the jug. No running. Okay, you good? So you're going to reach out and just drop that in the, you're going to reach. Big arm. Okay? Rest your body, look back a bit. Okay, ready? That's typically what you think of when you think of a combustion reaction. So if you aerosolize it like I did, that's all of the methanol igniting together. Do you have a video of that? Sweet. Lights back on. Top buttons. Cool. Oh, it's done more. More things have happened over there. You know, I have to clean all this up and get it going again for next one, so that's gonna be fun. Okay, last one. You know what? We got time. Let's do it. Okay, cool. Yes, this is the acid base.
Let's go. That's right. That's his next.
Yeah. Okay, so here I've got two. You can find this in your home. So vinegar, also called acetic acid, milk of magnesia. Oh hey. Yeah, sure. Milk of magnesia. This is an antacid. It's an active ingredient found in Tums. It also comes as a liquid, also a laxative, so it does multiple things. And this is called universal indicator. Doesn't have the label on it. That's okay. Oh, it does. Here's the label. Let's throw it up on the screen so all of you can see it. Tells you the pH at different colors. So let's start with, so the vinegar is going to mimic kind of what's going on in your stomach. You've got hydrochloric acid in there. So I'm just going to pour a bunch of this in there. Should use a smaller beaker, but that's okay. Seeing colors. Just going to throw this in the There we go. Figure yourself out. Okay, cool. So we're going to have some universal indicator. And I mean, vinegar is an acid. You'd expect it to be red. The pH of this thing is what? 1? 1-ish? So let's pour some antacid in there. The pH is changing. The pH was here, and you watched the color change. Now it's 7, 8? Yeah. No, it's almost blue now.
Almost blue.
So the pH, the reaction's happened. It took a little while for the reaction to get going. but the antacid reacted with the acid and it made now basic solution. Now, if I want to force it back the other way, I just grab more acid. And I can push it back the other way. We'll see how much antacid is still there. There's still antacid there. It's still going to continue to neutralize until the antacid is used up. It's going to continue to neutralize whatever vinegar I throw in there. There's yellow. How far back will it go? Back to green, blue. More acid. And react. It's happening slower now. But there's still plenty of MgOH. So what we've just created, the antacid, the milk of magnesia is this guy, MgOH2. The vinegar is this. So when these guys are doing their reacting, they're producing a bunch of water, H2O. And what's the salt that's being produced? In this case, the salt is what? It's going to be Mg, charge plus 2, and this polyatomic ion acetate is going to charge a minus 1. Oh, brackets. Yes, it's going to be Mg brackets CH3COO2. Not a salt you're probably familiar with, but I mean, one that your body, so if you did this exact same thing, drank a bunch of vinegar, which you could do, wouldn't be pleasant, but you could do it, and drank a bunch of this stuff, which is what it's designed for. This is designed to be consumed by you. This is the reaction that would go on in your system. It would produce magnesium acetate, which you would then, the laxative. So I'll let you connect the dots, right? Only if you added the universal indicator. The universal indicator is what's changing color. Great question, important detail. This is what's causing the color change. Yeah. The chemical formula for apple cider vinegar is the same, I think. There's the added, I mean, the apple is going to give it a different flavor, but the vinegar portion should still be, or is it malonic acid? Questions like that. What is apple cider vinegar? Apple cider vinegar. Oh, that's a TV series. Don't want that. Apple cider vinegar is 94% water, 5% acetic acid, and 1% carbohydrates. So it's the same acid. It's the extra carbs that give it a bit of flavor. Nothing done anything yet? No, we're just still hanging out. Okay, cool. So we've got the neutralization, double replacement, not overly flashy. This guy's still burning. So we come back over here. It's gotten bigger. That's cool. Love that. So now I have to figure out how I'm putting all this up next block. And I'm going to save, we've got one reaction left. The single replacement, which I am going to save till tomorrow. So if you're back tomorrow, tomorrow, or is it tomorrow ABCD? And it'll be last block tomorrow. I'll do another reaction for you. This one is going to be a little bit more dramatic, and this one we have to go outside for. So what I'd like you to do today for homework. Yeah, we're not going to do the lab tomorrow. What I'd like you to do, we'll save it to next week. What I'd like you to do is this. Find me this page in your notes, classifying chemical reactions. And all I want you to do on this page is identify, you don't have to do any of the balancing. All I want you to do is, based on the chemical equation that you see, tell me which of the 6 reactions are going on here. So your options are synthesis, decomposition, single replacement, double replacement, neutralization, combustion. You don't have to write the whole word. You can use the abbreviations they give you, SD, SR, DR, N, and C. And I'd like you to do the same thing with this guy. Do I have to do it twice? Nah, just do it the once.
all you need to do is tell me 30 questions, what reaction each one represents. I'll go over it tomorrow. That's your homework. Should not take you long. You could do it in another class, like English, for example. So you would probably love that. Okay, when the bell goes, you may also go have a great day. You can get the questions I just assigned. You can do it in another class. Like, I know how to do that. Get your homework. Basically, I just want you to get your homework done at this point. You have 30 questions, not hard to do. Get her done. But no balance. No balance. Tell me what kind of reaction. See you later, Sam. Okay. Fine. This is not as all I care about. All I care about. Okay. In a smaller beaker. Always fun, eh? Yeah, it's always fun. I enjoy it. How are you? Good. Do you want to change pace? What do you mean? Well, I'm actually you're the first person I'm down in the congratulations. Well, yeah, yes, no, I don't really want to. Looking after my mom. Oh, sorry. And moving, right? So that means my job is over. Really? No, seriously. They're getting advertising. I'm moving that house. You've been doing this kind of stuff, teaching one course at university. And usually overseeing how to do it. And congratulations. Sorry for the reason. Yeah, but you know. Well, I appreciate the heads up. I'm getting yeah, I know, but it's kind of good. Cynthia, I don't know if she talks to you guys about Greg and I both put in again. Oh, good. That's awesome. We're hoping to share one. Yeah. Just because neither of us want to give up a load. Yeah. So, I don't know if that's. So yeah, Greg and I put in. We love to share. Thank you. No idea why. I don't know what you're talking about. Don't know what you're talking about. No idea what you're talking about. I know nothing. Why would it smell like burning in here? I don't know. Okay. Yeah. Yeah. Come take a look. Maybe it is the same one.